Thank you everybody for joining us again. My name is Alex Bassini. I'm the Business Development Manager here at AWC Solutions. Today we're joined by Adam Jennings from Hach. We're going to be covering everything that has to do with nitrogen in wastewater. I know it's kind of an advanced topic from some of the ones that we've done before. Sometimes we used to cover wastewater kind of as a whole. For those of you that it's the first time that you're joining us, thank you again. This is a 12-part webinar. We're on number 9 now, so we're kind of covering a few of them at a time. And again, those of you that are new with AWC, we design and manufacture water and wastewater treatment plants. We keep them as modular as possible. Wow, we're popular today. There's more people logging in. Thank you, Matt, for joining. So we have both skid-mounted systems, and we have also both, this is, on the modular front, we do water and wastewater. Good morning, James.
Good morning.
So with that, we're going to turn it over to Adam. We're focusing primarily on the nitrogen and wastewater and how to identify it and how to monitor it as well. So go ahead, Adam, take it away.
Yeah, thanks, Alex. Is my screen showing?
Yes, we can see it.
Nitrogen and wastewater. Well, thanks for having me today. I really appreciate the opportunity to chat with you all today. Like Alex said, we're going to go through some nitrogen application and a little bit about nitrogen and wastewater. Hopefully there's a little bit for everyone at all stages in this conversation, but we'll get right into it. So I'm going to cover why we remove nutrients specifically and wastewater biological zones, because when we're talking about nutrients, it's really important to kind of understand the background of where we're treating in our wastewater treatment plants and how that occurs. And it can be a little bit more simplified by breaking it down into the biological zones inside of a wastewater plant, rather than talking about all of the different types, MBBRs and MBRs and activated sludge and all that. We can simplify it a little bit. And then we'll talk about process monitoring application practice. So why nutrients? Well, nutrients in the environment causes a lot of various issues from environmental toxicity. When we're talking about ammonia, particularly, ammonia is toxic to aquatic life in relatively small concentrations, which is why our treatment plants have a lot of treatment plants greater than 4,200 have nutrient permit numeric limits currently, and another 5,700 treatment plants in the U.S. are required to monitor for nutrients, whether it be nitrogen or phosphorus. So it's on everybody's mind, and it causes a number of problems. Eutrophication is another issue that occurs with higher or excessive amounts of nutrients, nitrogen and phosphorus in the water. And you can see these pictures, some pretty substantial algae growth, and that algae, when it dies off, causes oxygen depletion. And then you can see on the left, you could end up with situations with large fish die-offs, and you may have heard about those in the news in the past. And another issue is, with nitrates, particularly in drinking water systems, can be really harmful to young ones, babies. So water body impairment and designated use control for each NPDES permit is what EPA is looking for when they're giving us these regulations, in the US anyway. So wastewater biological environments, or zones as we call them here a lot of times, when we're talking about wastewater treatment plants, like I said, there are so many different ways and terms: activated sludge, plug flow, step feed, MBBRs. There's so many different technologies out there, but really it can boil down into 3 very specific biological zones: anaerobic, anoxic, or oxic/aerobic, depending on how people are terming it. And what we're doing is we're managing bacteria in a certain manner, with or without oxygen, with or without combined oxygen, free oxygen being O2, and combined oxygen being something like nitrite or nitrate. And so when we're talking about dissolved oxygen, and as it relates to an anaerobic zone, and combined oxygen, as it also relates to an anaerobic zone, dissolved oxygen is not present in an anaerobic zone. It shouldn't be. Combined oxygen also should not be present in a true anaerobic zone. Now, in our wastewater treatment plants, sometimes this is very difficult with return streams, such as RAS, return activated sludge from a secondary clarifier, can have nitrates. But hopefully we're anaerobic in the true sense. So if you have an anoxic zone, a zone that doesn't have any free oxygen also, but it may, and it most likely does, have the presence of combined oxygen, nitrite, nitrate, or other combined forms of oxygen. This is very important for the different stages of nitrogen removal in wastewater. And then, of course, the oxic or the aerobic zone, where you can see bubbles coming up in a wastewater treatment zone that has free dissolved oxygen. But does it have nitrite or nitrate? We don't really care, because at that point the bugs have everything they need. They're opportunists and they have free dissolved oxygen to metabolize and respirate. So nitrogen, there are so many forms. There's a number of forms of nitrogen, and when we're talking wastewater treatment, we may have particulate organic nitrogen, soluble organic nitrogen, ammonia nitrogen, nitrite, nitrate. And the way we kind of group these up, we tried to describe here a little bit, in the organic forms or the inorganic forms. Maybe total Kjeldahl nitrogen is something we're tracking, but the total nitrogen encompasses all of these various forms and terminologies. So when we're talking about the forms of nitrogen and wastewater treatment, you may have heard the term or are very familiar with nitrification, denitrification, and this is something that occurs naturally in the environment. But in wastewater, depending on what the end goal of our treatment processes are, we may be trying to remove ammonia, and we may also be trying to remove the other forms down to nitrate. And so when we're looking at wastewater treatment, there are two specific zones that I want to bring up right here as it relates to nitrification, denitrification. The top half of this explains or kind of visualizes an aerobic zone, a zone that has oxygen present. And the bottom half of this line would describe an anoxic zone, which is where denitrification would happen. And so, in a wastewater treatment plant, the main form of a typical municipal wastewater treatment plant would be ammonia as far as nitrogen goes. And there may be some differences for an industrial application, but for the most part, ammonia is what comes in, and autotrophic bacteria are converting to nitrate. And then once this liquid moves into an anoxic zone, a different type of bacteria can transform it to nitrogen, all the way through to nitrogen gas. And there's a couple of forms listed there. Point being here is that we're removing nitrogen in the form of a gas rather than a solid, like you would with phosphorus. So a point on nitrification: it consumes consumes oxygen and alkalinity. And denitrification consumes carbon, but it also creates alkalinity. Alkalinity is key, as we'll talk about a little bit here as we move forward in the nitrification process. So this is just a quick depiction of what might it look like with as it relates to the concentration of a nutrient moving through a wastewater treatment plant and the various zones we talked about. So on the left, you have an anaerobic zone, and then an anoxic zone, and then an aerobic zone. And ammonia would typically move straight through without much degradation until it hits an aerobic zone. So there's no bacterial degradation of ammonia in an anaerobic or anoxic zone. But as soon as it has air, these certain types of organisms will metabolize ammonia and turn it into nitrate. And you can see how the relationship, if you look at the blue line across the bottom, is nearly a 1-to-1 relationship. As these bugs consume ammonia nitrogen, it turns it into nitrate nitrogen. And these slight changes in the anoxic zone are due to an internal mix liquor recycle, which may be available in some cases, which brings that nitrate-rich liquid back to an anoxic zone to remove it in the form of nitrogen gas. So What that looks like in practice, hopefully this animation works for us. You have ammonia coming into an anaerobic zone. It moves through from a biological standpoint without much change, and then it gets converted to nitrate in the end. And if you have a internal recycle, it is brought back around to this anoxic zone and then removed as a gas. So anoxic conditions, a couple of points, these bacteria are opportunists. So if you are trying to meet a total nitrogen limit in the effluent of your treatment process or reduce your nitrates, then you must have an anoxic condition that is free of dissolved oxygen. So if you have an internal recycle that brings oxygen back because it's poorly placed or there's too much oxygen being brought around, then it can inhibit denitrification. And DO represents free oxygen, of course, in contrast to the combined forms. And DO present in anoxic zones reduces the nitrification capabilities. And if you're using ORP, you may be looking for values, and we'll talk a little bit more about these particular instruments as we get a little farther along. But if you're using ORP, millivolt values between 100 and minus 100 would represent generally an anoxic condition. So if we're talking about aerobic conditions and some of the key points that you might see, when we're talking about nitrifiers, we're always looking to see how much oxygen they need. And in many cases, we just describe it as much as they need. There are times when we may not have air in specific zones, and so nitrification doesn't occur. There are typical DO, dissolved oxygen values in an aerobic zone between 0.5 and 1 milligram per liter is difficult because you might be inhibiting nitrification at low levels, but also can grow certain types of organisms that cause challenging effluent quality as far as turbidity goes or excessive solids because it grows filamentous bacteria. And some interesting points, nitrification, the nitrification cycle consumes 4.57 pounds of oxygen per pound of nitrogen oxidized. And if we're referring to ORP values in an aerobic zone, we will be looking at positive millivolt values between 300 and 100 millivolts. So real quick on this slide, there's a little bit more going on here. Just ignore the red line, phosphorus. That's for a topic for another day. But I wanted to just touch on, aerobic conditions and dissolved oxygen demand. So as you can see here at the front of an aerobic zone, as depicted by this triangle at the top, the demand for oxygen is very high at the front end of an aerobic zone when we're nitrifying. And as it moves across, as the flow moves through this zone from left to right, the demand for BOD decreases, biochemical oxygen demand, which ammonia nitrogen is part of that. And so, as you can see, sometimes in treatment plants, we over-aerate, or we have so much capacity because our flows at various times, diurnal flows, overnight the flows drop off and the loading drops off, and so we may over-aerate. And over-aeration can cause a number of issues that could be a whole topic all on its own. But just to describe the idea here in general terms, if we're aerating the last half of this zone or for a long period of time after the DO demand is gone, we're just wasting energy. And aeration is the highest energy consumption that happens in a wastewater treatment plant. So spending a little bit of time on a simplified version of a wastewater plant, you can see the influent would come in from the left side of this diagram into an oxic or aerobic zone, and then move into, say, a settling clarifier at the end of the process, and then out to the effluent. And this bottom line represents return activated sludge. So if you have a facility that has a suspended growth solids, such as activated sludge, then a settling clarifier can be used to move active biomass back into the process for more treatment. And so when we're talking about instrumentation, what can we do to help ourselves be efficient in wastewater and monitor and optimize our process. We can use various probes and instrumentation, and so I'm just going to go through a number of things from an oxic aerobic perspective, and then on the next slide we'll cover a little bit more about an anoxic condition monitoring. And so here, pretty classic, and many people will be familiar with the optical DO probe that can be used. If you have a large basin, you might need multiple DO probes to monitor dissolved oxygen because, like chlorine, we want a residual of dissolved oxygen at certain concentrations that meets our treatment limits. And so when we're talking about dissolved oxygen, there are a number of different ways that we can control it and use that data. These dissolved oxygen probes can be used to stage blowers on and off and turn the speed of blowers up and down. And that can be done automatically with a program based out of Hach's new line of RTCs, real-time controls, that can control out of the box your aeration system if it's capable, if you have valves that are in the system to modulate airflow and or 50 or multiple blowers to stage on and off. These all can be controlled by these real-time controls from Hach. We talked a little bit about alkalinity. pH is a really great low-cost spot check to understand where your pH is in an oxic zone. And again, the reason why we care about pH in an oxic or aerobic zone is because the nitrification process consumes alkalinity. And so we need a certain amount of alkalinity to properly treat for ammonia nitrogen. And if that alkalinity gets depleted too low, if the battery runs out, then we could end up in a situation where we are unable to nitrify and remove ammonia nitrogen. And so pH is a great lower cost spot check. But in treatment plants that have constant issues with pH or alkalinity, we recommend using a wet chemistry analyzer that measures alkalinity as the actual parameter that we really want to measure. And alkalinity is like a battery, and once that battery gets really low, we end up with a pH depression and lots of issues with biological function. So moving along, we add a TSS probe. So TSS stands for total suspended solids, and this probe will measure the solids concentration in various places. And in this particular case, we have one located in the basin. It could also be located as it leaves the basin to a clarifier. And the idea here is that there are a number of controls that we use that are contingent on the solids concentration. We're using controls such as food to microorganism ratio that rely on this value. We're looking at potentially pounds under aeration, or even more specifically and more accurately, SRT. Solids retention time is an industry-leading measurement that helps us understand where our process is and what is working and what is not working in certain conditions, whether it's cold outside, changing conditions, warm, hot, flows are different at different times of the day. And Hach has a solution that can help pull all that together. Instead of manually calculating SRT, we can use a real-time control that will optimize the wasting and control the SRT for you in an automatic function, or simply present it as a value to be used as a guideline for manual control. Ammonia nitrogen, of course, is one of the main topics of today, and so we would be remiss if we didn't add in some clean understanding and capture of what's happening throughout a 24-hour period, what's happening when it gets cold out or when it's hot or we have changes in our process. Are we constantly nitrifying properly? Well, using wet chemistry analysis, we can get down to very low levels, extremely accurate and easy to maintain ammonia values at the end of an aeration basin. And if we add in an ion selective electrode for ammonium as well, these two things combined with a solid sensor can create a situation where we can add in a RTC for nitrification, denitrification, where in this particular case, we may not even need to use DO anymore for control. We can use ammonia as a feed-forward, feedback, tightly controlled system, and only aerate as much as we need for proper treatment. So secondary clarifiers, we have blankets in secondary clarifiers, and one thing to note is that there is great instrumentation out there to help us manage in real time what the blanket level is with the Sonotax from Hach. And then as we move through the process, we're checking what's coming out of aeration systems. And if we have multiple trains, we may be wanting to measure what's coming out of the entire system, multiple trains leading into one pipe that then heads to the effluent. We want to understand what the nitrogen content, ammonia nitrogen content is going out, as well as potentially total suspended solids. And all these data points, when we start adding instrumentation and controls, and we're starting to get data, the data that we capture is maybe not of value if we're not looking at it in a way that makes sense to our operators or to our plant managers, engineering groups. And so we have a system that takes all of these data points, whether it be from handwritten information that can be converted into forms that are put into an electronic repository, or we're taking all of these data points coming from these probes and turning them into and putting them into one place. The SCADA system and the laboratory, we're getting all this data from various places, and having it all in one place in a way that's really easy to see and understand can all be captured with the Hach WIMS collect system. The WIMS is our data management system that takes so many different locations where data might be kept or managed and brings it into one location so that the data can be manipulated and managed in a clean and visual function. And then as we move into the finer points on the top right here, we would be lacking, if we didn't talk about the laboratory. If we have operations laboratory, or if you have an on-site laboratory, all of these parameters that you see here and many, many others can be managed and properly tested and analyzed with Hach DR 3900. Various things like COD, TNT, ammonia, simplified TKN, alkalinity. We have field probes that are handheld to spot check your equipment from LDO or pH, portable TSS, and all of these things help complement and help you manage your online probes that are in the field. So all of these high quality lab equipment can be very complementary to your process instrumentation. So final and last slide, just working through again, we still have some of these probes and analyzers on this screen, but if we have added an anoxic zone for selecting out filamentous organisms, or in the case of nitrogen for denitrification, we talked a little bit about ORP. Again, ORP is very similar to pH in this application, where it is really great for a low-cost option to give us a ballpark understanding of what might be happening in an anoxic zone. And one of the things that we try to recommend then, if you've understood what's going on from a general sense with ORP, because of all of the potential influences from other chemistries in the water, we recommend for very tight analysis of specific functions as it relates to denitrification to use a UV parameter, which measures the actual parameter, or an ion selective electrode in this location. So therefore, we're measuring the actual parameter rather than a surrogate in the same manner as we were with pH. And this provides a much more accurate reading and response, especially if controls are desired. And so there are ways that we can use the Hach systems for real-time control to also control the internal mix liquor recycle based on nitrate values in an anoxic zone. simultaneous nitrification and denitrification for ditches and various other systems. RTCs for SBRs and biological nutrient removal are available as well. And then at the end of the process, if we add an anoxic zone, we may be concerned about total nitrogen. And so on the far right, this is a wet chemistry analyzer from a newer series by Hach that has individual parameters such as total nitrogen, total phosphorus, and in this case, this particular analyzer can do 3 actual analysis: total nitrogen, nitrite, and nitrate, which is another form that we haven't talked too much about today with as it relates to nitrogen. And this unit can also be programmed to do total Kjeldahl nitrogen, and all of these individual parameters can be 4 to 20 output, set up with 4 to 20 outputs for SCADA historical trending and other controls. So rounding out the conversation, we're looking on the right here again. We have a nitrate probe if the wet chemistry analyzer is not needed. And then at the far left, the influent, when we're talking about loading coming into a treatment plant, it may be good for us to really understand changing conditions as it relates to organics, biodetector, and or probe for total organic nitrogen or SAC. And then again, just to finish it out, the laboratory data is available on a DR3900. There's also a DR6000 for those treatment plants that are doing UV disinfection and are concerned about UVT. The DR6000 can do a tabletop spot check and calibration of the turbidity to compare with online upstream UVT probes that control various UV systems. So that's what I had today on nitrogen. I hope that this was helpful, and I think we're looking for questions in the last few minutes here.
Thank you, Adam. That was great. I warned everybody this was going to be more on the advanced for the wastewater side. We've already touched some of the modular wastewater options that we cover on the membrane bioreactors and the MBBRs, but this was primarily more on taking a look at nitrogen and how we monitor it. If anybody has any questions, you can stick around. We're right on the 24-minute mark, so I know everybody's pretty busy and they can kind of get back to work. I do have a couple questions here that somebody typed in, and then I have a couple questions of my own, so I can go ahead and open the floor. Don't be shy. You can turn on your cameras and ask a question, or if you want to pop it into the chat box. I did have one question here. If you go back one of your slides, you had mentioned you were testing for total suspended solids inside of the aerobic zone. Is there a reason why you wouldn't test it on the outlet or the effluent coming from the aerobic going into the clarifier?
No, it's a great question, Alex. No, there's no reason why we can't test there. And in fact, that may be, in some cases, a better location. The reason why we show it here is that these some facilities don't have the ability to access that pipe or that location, and so it may be easier in some cases to put it at the end of an open basin, if you will, like it's shown here in this particular situation. But this particular TSS probe also has the ability to go in pipe at pretty substantial pressures. So as long as those pressures and the application is appropriate, it can be put into a pipe with great success in that location. So yeah, good question.
Okay, well, thank you very much. We use a lot of the remote monitoring and some of the sensors through Hach with both our potable water and the wastewater. And as everyone can see, there is a lot of monitoring when you go into wastewater. It's not just taking a look at your ORP or TSS. There's a lot more to it. So with that, if anybody has any questions, please come forward. If not, this will be published on the YouTube channel in the next 48 hours. We're trying to not do too many editing, and try to get that out as much as possible. For next week, here I'm going to pop up my screen here for a second. For next week, we have Chuck. Chuck's going to be joining us, and he's going to be covering some of our dosing pumps. So not just ours, but he's going to be looking at different dosing pump alternatives, along with some chemical metering and some of the different pump options that are out there. Hey, good morning, Troy. So I do have one more question here from Mark here. I don't know if you can read it there, Adam.
Let me take a look. Yeah, could you please expand on the use of the intermittent aeration for SND in a continuous process? Yeah, so the SND process is designed to either turn the air on and off inside of an aeration zone, or stage it at different levels so that it can be, so that when you reduce the aeration in a certain zone, if you have multiple zones of multiple aerated zones, banks 1, 2, and 3, if you will, for systems that have that, the system can be staged where it turns on and off or reduces air to those particular zones, especially if they have controls in place, such as valves, actuated valves for those locations. And so it has a number of different abilities to control how that air is turned on and off. And basically we're doing nitrification in the front of the aerated zone, and then potentially as you start moving through and reducing the air through an aerobic zone, then we're getting some denitrification as the air drops off in certain stratas of the aeration or the oxic zone itself.
Question.
Go ahead, Troy.
Yeah, hi, Adam. Great presentation. Question of the day is on that probe that you've got on the RAS line on the secondary clarifier, how accurate is that? And can you translate that into a really good mixed liquor concentration? So one of the things I've seen in a lot of plants is really operators struggling with, a return that has a consistent RAS flow.
Yeah.
Due to flows and temperatures and whatnot. But one of the issues is getting air back into it. How accurate can you get that mixed liquor on that TSS probe?
Yeah, it can get, it's really accurate. And in fact, many on the call may not know that I came from the wastewater operations and management field. So I operated these actual devices before I joined on with Hach, which is part of the reason why I got on this road. Is the TSS probes, the Solitax, really great products. I've used them in mixed liquid applications, open channel, and also closed pipe situations, and it works really well to help give you a really accurate 24-hour diurnal picture of what your RAS is doing, and then also what your what your mixed liquor is doing. And to your point, it is key because most of us have places around the country and around the world where we have changing conditions, and managing our solids is key to operating within our permit limits on a consistent basis. So lots more to say on that as well, but I don't think we have time to cover it. But absolutely, yeah, it's worked really well for me in the past, having used that equipment. So.
All right, thank you very much, Adam. That's enough for time for questions for today. If anybody else has any questions, we have Adam's email on there, so you can shoot him a quick email or send one to me. Again, this is going to be available up on our YouTube channel shortly. And if you don't already follow us on LinkedIn, go ahead and follow us on there. You can see AWC. We've got a pretty active community, and we share a lot of these events that are coming up. So thanks again, everyone, for joining us, and see you next week. Thank you, Adam.
Thanks.